Hi everyone. So in this video, I'll be talking about a device known as manometer. So the primary function of this device is to measure the pressure of gas. Pressure of gas. Which gas am I talking about? So let's look at the setup of manometer first. Okay, this is the setup of manometer. So in this setup, you can see that there has been a gas that has been filled in the manometer, and it has been also been filled with mercury. So this is basically this liquid, especially in this region. I'll just mark it down. Let me use some blue color. So this liquid is basically mercury. Okay. uh, so manometer has two kind of arms. One is the longer arm and the other is the shorter arm. The shorter arm consists of a gas, usually the pressure of which we are trying to figure out what should be the pressure of the gas that has been trapped in this shorter arm. And the longer arm consists of mercury, which is open to the atmosphere. So from this diagram, two things can be observed. The first thing is that the longer tube rather, consists of mercury, and that particular longer arm or tube is subjected to atmospheric pressure. It is subjected to atmospheric pressure. And secondly, it consists of a shorter arm or shorter tube which has the gas, okay, and it is subjected to the pressure of the gas. Obviously it is subjected to the pressure of the gas. All right, so this is the basic layout of a manometer. The objective or a function of the manometer is to measure the pressure of gas. First kind of manometer that we are going to study, it is called closed end manometer. It is called closed end manometer. Okay, the reason it is called closed end because the longer arm or the longer tube which was supposed to be exposed to atmosphere, it is actually closed. Okay, and this particular region will ideally should contain vacuum in it. Okay, there could be a gas trap, then we need to consider that pressure of the gas as well, but as of now we are considering it to be ideal manometer, so therefore we have considered vacuum in that region. All right, now we need to figure out what is the pressure of the gas in this manometer. All right, that is the main objective. All right, so let us use the fundamentals of pressure that we have studied in the part 1 and the part 2 of the video. So if you have not seen the video, please, I will probably be attaching the link in the comment down or in the description below. You can go ahead and look at the part 1 and the part 2 of the video and continue with this part of the lesson. All right, so now let's consider a few points in this diagram. Let's consider point A that already been marked, point B, and let's take one more point as C. Okay, all right, so if anybody is unable to follow the diagram, this part of the region is the gas. Okay, so I'll just use a different color so that you can understand that and distinguish rather the different regions. So this part is the mercury. Okay, this part is the mercury, and rather I should say the pink part is the gas. All right, so this is the gas. So if I have to understand or rather compute the pressure at point C, it should be equal to pressure of the gas. Alright, the reason I'm saying that pressure at point C will be equal to the pressure of the gas is because the pressure of the gas is uniform throughout the entire container it is kept in. So no matter if the point is at this, if this is C point, or this is C point, or this is C point, or this is C point, irrespective of where the point is, the pressure in the entire column should be equal to pressure of the gas, because we have considered the pressure of the gas will be uniformed in the entire part where the gas is kept. Alright, okay, now according to the rules of the pressure that we have studied in the I think in the part 1 of the video, pressure at point C should be equal to point B because they are in the same horizontal level. Alright, so pressure at point C should be equal to pressure at point B. Alright, now pressure at point A, let's talk about pressure at point A. Pressure at point A will be 0 because this entire region is vacuum. Alright, because this entire region is a vacuum and pressure at vacuum is 0. Alright, now let me calculate the pressure at point B. Pressure at point B will be due to the liquid column, liquid mercury column above it. So pressure at point B should be equal to rho, that is density of the mercury, multiplied by G, which is the acceleration due to gravity, multiplied by the H. And pressure at point B is also equal to pressure at point C, and that is also equal to pressure of the gas. So from this I can conclude that the pressure of the gas is equal to density of mercury multiplied by the acceleration due to gravity multiplied by the height of the mercury column. You can also, just by looking at the diagram, figure it out that the more the pressure of the gas, it will exert much higher force on the liquid mercury, and if the force on the liquid is higher, the liquid will rise to a height h because of that force. Alright, so this is why there is a increment in the height, okay, because of the pressure of the gas in it. Alright, so this is the second kind of manometer. This kind of manometer is called a open end manometer. Okay, the reason it is called an open end manometer is because one part, or the longer part rather, manometer, because the longer end of the manometer, which is basically this particular region, longer arm of the manometer, is exposed to the atmosphere. That is why it is called open end. Alright, so I'll just, okay, so there is a stopper over here. Okay, so I have there is a gas that has been stored inside the manometer, and okay, so let's understand what is the function of an open end and when exactly it is used. So open end manometer is used again to measure the pressure of gas, but it is used when the pressure of the gas is either going to be less, when it is less, equal, or higher rather than the atmospheric pressure. Again, so here we are trying to figure out the pressure of the gas and we are comparing it with the atmospheric pressure. So that is the benchmark. The atmospheric pressure becomes the benchmark, and we are trying to figure out the pressure of the gas with respect to that benchmark. Alright, so this is the only difference between the open end and the closed end manometer. So in the closed end one, the only way to figure out was the height of the mercury column. Here we are kind of comparing it with atmospheric pressure. Alright, so this is the case 1. Okay, so this is the case 1. I can just write it down. This is the case 1. In the case 1, the concept is pretty straightforward. The height of the mercury column is coming out to be at x dash. Alright, so we need to figure out the pressure of the gas. So again, you'll use the same idea that the pressure at x dash should be equal to P atm. and that should also be equal to the pressure at x. The reason being, the level of x and x dash are exactly equal. Alright, the pressure at x dash is equal to the pressure at x because they are at the same horizontal level. Okay, acha. Now what exactly is the pressure at x? So I can say that if you zoom in carefully, the pressure at this point, if I take, let's call it A, and the pressure at this point, I can tell that the pressure at these 2 points are equal. Okay, because they are at the either side of the x. So pressure at A is nothing but pressure of the gas. Okay, and this is also equal to the pressure at B. Okay, so I can just directly say that pressure at x is equal to the pressure of the gas. All right. Now let's talk about the third case. So the third case is when the pressure of the gas is going to be greater than atmospheric pressure. Okay, so if you look at the diagram very carefully, you will observe that the longer arm of the manometer has a elevated level of mercury. Alright, so this might be due to the higher pressure of the gas in the shorter arm. Okay, now let's look at this diagram very carefully and try to understand how the pressure is varying. Now let's take 3 points on these diagrams, A, B and C. So you can see that the pressure at point A will be atmospheric pressure. So the pressure at point A will be atmospheric pressure because A point is exposed to the atmosphere. Okay, now we are moving to the point B. So as you move from point A to point B, we are decreasing the height of, we're going downward by a height of h. So whenever we go downward, pressure increases. So pressure at point B will be equal to P atm plus rho of mercury multiplied by G multiplied by H of mercury. Alright, now pressure at point B will be equal to pressure at point C. Okay, now if you look at carefully, pressure at point C will be equal to the pressure of the gas. Pressure at point C will be equal to the pressure of the gas because at point C, if you zoom in a little bit, pressure, if I take point C above the liquid and below the liquid, there won't be much pressure difference. So I can say that the point, if I take a point above the liquid, it should be the pressure of the gas, and the pressure of the gas is going to be uniform in the entire container where the pressure gas is kept. So no matter at what point I take in this container, pressure of the gas will be equal at all these points. Alright, so I can directly say that pressure at point C is pressure of the gas. So pressure of gas will be equal to pressure P atm plus rho GH. Alright, so you can look at the equation. You will observe that pressure of gas is equal to atmospheric pressure plus some x, which is rho GH in this case. Alright, so this kind of a setup is observed when the pressure of the gas is greater than the pressure of atmospheric pressure.